Welcome to the second half of the second lecture in the 8-week course on Computer Algorithms 1. In the first half, we said that an algorithm is efficient if, is, if its asymptotic running time is bounded by a polynomial function in the input size. We are interested in how algorithms scale when we are, say, doubling the input size. Um, so we defined asymptotic growth. We introduced the big O, the big theta, and the big omega notations. Big O, big omega, big theta for the asymptotic growth. In this lecture, in the second half, we will demonstrate some properties which are very useful if we are reasoning about asymptotic growth of the running times of algorithms. But let us start by some canonical examples of running times. Here are the different examples that we will consider. Sorting is very important because in a sorted sequence one can search very efficiently in time that is logarithmic in the input size. Binary search works extremely quickly. Finding the maximum in a sequence that is not sorted, in an unsorted sequence, takes a linear time. N log n is important because it is the time to sort a sequence. There are also quadratic sorting methods, but you don't really want to apply those methods on very large sequences of, say, a million numbers. For quadratic time, consider computing the smallest distance between points in the plane in a very straightforward matter. Cubic time, look for the common elements in sequences of sets. This is a course focused on discrete problems, so I picked discrete problems. If you have an interest in linear algebra, then quadratic time is solving a system with a matrix that is triangular. Cubic time is reducing any matrix to a triangular form. We can make any algorithm that runs in time n to the power k, so it's still polynomial time, but the exponent matches here the size of the subsets we are searching through. And then we have the brute force searches. These are typically exponential time. We will end the list of examples with coming back to the brute force search for the solution of the Gale-Shapley algorithm. Okay, here is the binary search um, algorithm. We formulate it as an outcome that is true and false, so there's only one bit that is returned. Given on input a sorted sequence and a number, and we want to decide if that number belongs to the sorted sequence or not. We pick the middle element. We are checking whether the middle element is the element we're looking for. If not, we continue in the second half if the number we're looking for is larger than the middle. Otherwise, we set the search space to the first half. The reason why this is sublinear time or logarithmic time is that the search space is cut in half in each iteration. So you see the stop condition is as long as there are still elements in this list. As long as the search space is not empty, we continue. So in a list of 1024 elements, you can be sure to find your number, if it's in there, in no more than 10 steps. And 1024 is 2 to the power 10. A million numbers, 2 to the power 20, 20 steps. So these are algorithms that scale extremely well. Okay, linear time. Here we consider an unsorted set of numbers, and we have to go through each and every element um, to decide whether to find the minimum. So here to find the maximum. Sorry, this is not a decision algorithm now. So we have to do a number of steps that is proportional to the size, that is actually equal the size of the set. We have to walk through each and every element. Now, n log n time. So n log n, suppose if you have never seen sorting algorithms, this looks very strange, but I hope to demonstrate with only 2 slides that the n log n time comes up in the running time of merge sort. So suppose we want to sort a sequence of numbers. How can we do this? Well, we cut the sequence in half, sort the first half, sort the second half, and then we merge the sorted sequence. So we pop from the sorted sequences first half, second half, each time the smallest element. And you have to go through the entire sequence, go through all the elements of the first half, all the elements of the second half to do this merge. Sorting said, well, we don't actually know what the time is. We have the capital T. That is the function that indicates the time it takes to sort n numbers. So sorting half of the numbers takes t evaluated at n over 2. So we can say that for any size, the time it takes to sort is twice the time it takes to sort a sequence half of the size, plus the cost for the merge. So that is the recurrence that we have derived here. In some sense, you could see it shares the resemblance with the binary search, that the size gets cut in half, but we have this factor n sitting there, n times the logarithmic. And why is that? Well, here is a proof, or the outline of a proof. We will work by induction on the number of elements. So how does a proof by induction work? We consider first the base case. A base case that consists of 2 numbers. You could say the trivial case is just one number, but one number, the 2 log of 1 is 0. Notice that we want to state that O of 2 is O of 2 as well. So we cannot say that O of 2 is O of 0. Then, so the base case is the first important step. You verify on the smallest case that makes sense, the smallest input, you verify that the property holds. If it doesn't hold, then you're done actually. Yeah, but you cannot continue. Then we take the induction step. So we assume that it's true for all sizes strictly less than the input size. Then it's also true for half of the size. So now actually we know that half of the size takes the order of n over 2 times the logarithm of n over 2. And then we apply the induction step. The induction step is combining the result of the induction hypothesis. So we sort twice, two halves, and we do the merge. So we have the n coming in there. Okay, and then, so in some sense, we are not done yet. So we know that the logarithm is actually strictly increasing. It's slowly increasing. So the O n log n time is an upper bound for linear growth. So we have that we can safely ignore the O n time. Adding two O n log n's is again an n log n. And we use the property of the logarithm that if you have the logarithm of a quotient, you have the difference of the numerator and the denominator. And this all implies that the cost of merge sort is n log n. So in some sense, you may have seen this in a course in discrete math already in solving recurrences. What I want to do here is essentially showing what is a proof of induction and also introducing the properties of working with big O notations. We actually here are seeing a specific case of the sum of two big O's. Quadratic time, so we consider point sequences, sets of points given by integer coordinates. So this is in a discrete setting. And we want to compute for all the points in the set, find those 2 points that are closest to each other, or actually compute the minimum distance here. So here is the straightforward manner of doing this. So there are better ways of doing this. We're going to see divide and conquer algorithms. You can do this better with the divide and conquer strategy. So here I'm just interested in giving an example of a quadratic time for a discrete problem. So the input size consists of the n points. So you could say that the input size is actually 2 times n. But since this is linear time, it doesn't really matter. So how do you see that this is linear time? I was almost, that this is quadratic time, I'm sorry. So it is quadratic time. How do you see that this is quadratic time? Well, you observe the double loop. That's the main point. You could say that by symmetry, you have actually, you can do better. So if you actually could order the points. Instead of a set, you have a list. And if you have checked the first point with the second point, you don't really need to compare the second with the first point. That's an obvious optimization, but it is still, and here I can use the opportunity to introduce the lower bound that we have defined in the first half of the lecture. 1/2 times n square is still big omega of n square. So this algorithm, by comparing all possible pairs of points, even with cutting the number of comparisons in half, you don't really reduce much in the asymptotic costs here again. In practical purposes, you may want to do this optimization. Okay, cubic time. Cubic time, consider a sequence of sets of numbers. And you want to look if in this set of numbers, this collection of the sequence of sets, is there a pair of sets that share no common element. So you can see the three nested loops. That is actually the motivation for getting to cubic time. And here again, the capital N is actually the input size. But then again, so it could actually, if you are strict in the input size, if you have to compare all elements of sizes N, then it actually would even be a quartic in the input size. So I'm here a little bit inconsistent with the notation. Now there is the extra if. It could be that if you compare the first two sets in your sequences, you already find two disjoint sets. But we are interested in the worst case, in an upper bound in the asymptotic uh, running time. Okay, now finding an independent set of size k in a graph. So we will spend plenty of time on graphs in lecture 3. So we will introduce graphs there, and throughout the course we will introduce more on graphs. A graph is a set of nodes, and a set is independent if no two nodes in the sets are joined. So you have a set of nodes that are independent from each other. If from first set and the second set, no two nodes are actually joined by an edge. So in order to solve this problem, you have to run to all subsets of size k. And this is done by this n choose k. So the n choose k evaluates as this quotients. So we have the k factorial in the denominator, but notice that the k factorial is a constant, independent of the capital N. So the k factorial will grow, and it makes sense to ask this for large values of k. So it can still be very large, but the k also appears in the exponent. So it's important here to make a clear distinction, which is the variable, the input size, and or the dimension, um, and compare this to the what is constant. Beyond polynomial time, so I'm almost 20 minutes in to this lecture. Looking at examples is very important. Here you see the brute force search. In lecture 3 we will actually go for algorithms in a brute force search. We will enumerate all possible perfect matchings. So we have to check for every employer all possible applicants. For the first employer, the second employer, third employer, also all possible applicants to consider. So there is the n factorial that comes in very naturally. So enumerating all possibilities of all possible pairings uh, will take you n factorial steps to consider. Now n is here the dimension, not the input size. The input size is quadratic in the dimension, so we have the list of preferences, two tables of preferences. So we can actually reformulate this in the factorial of the square root of the input size divided by 2. But this is also of the order factorial. If that causes some doubt, remember the first exercise in this lecture. So it could be a redoing of the first exercise, actually show that this factorial cost, that is actually uh, an upper bound. So the short answer is again that the square root is a monotone increasing functions. And with the big O, we're interested in upper bounds. Taking the factorial of, say, 2 and 4 matters a lot, but it's still the big O, asymptotically. Okay, properties of asymptotic growth rates. Let us look at the transitivity. So if you have a function which is O of another function, and that other function is O of a third function, then that first function is actually big O of the third function. So this looks, um, so in some sense, the purpose of the proof, going through the proof, is very good to the application of the definition, and also to appreciate the shortness of the notation of the big O. So what does it mean for a function to be big O of another function? So there is the constant, there are actually two constants, little c and a capital N naught. It's it's capital N, but it's independent of the problem size. So it is a constant. So we have that for all input sizes larger than the uh, constant N naught, our function f is bounded by the constant c times that g function. Now you do that too for the function g, but within the context of a proof, we shouldn't assume that we have the same constant, so we have to pick another letter for the constant d now, and we have a constant m naught. Okay, so this is the input. Then we have to arrive at the then. What we do is we pick the largest value. I could have worked with an other upper bound, but we take the maximum of n naught and m naught. So we have these two properties. So we have that f is less than c times g of n, and g of n is less than d of n. So putting everything together actually implies the statement of the theorem. Quod erat demonstrandum. Okay, so repeat the proof now for the big omega. So the purpose of this exercise is that you look back at the definition of the big omega. And you can use exactly the same structure of the previous theorem. There are 3 sentences in there. You copy these 3 sentences and you adjust them for the definition of the big omega. The consequence is that if you have tight upper bounds, big theta, for f, then actually the transitivity implies that if you have that every every 3 of the functions is actually has the same function as the tight upper bound. So all 3 functions are of the same order. You could have this if you have 3 quadratic polynomials for f, g, and h. Okay, sums of 2 functions. So in some sense, this was a generalization of the proof for the O n log n for the merge sort. So if we have 2 functions f and g, they are both of the same order, h. Then their sum is also of the order h. How do we see this? Well, we write down the definitions. What does it mean to be a big O? And we are careful to choose different constants. That could be if you apply definitions too literally, you apply the same letters. So the virtue of these proofs here is that you have to be a little bit creative in choosing the names of the constants. But then the conclusion, the third sentence here follows by the application of the first two sentences, and then also uh, referring back to the definition of the big O. So for the sum, we have the maximum of the n naught and the m naught, and we have the sum of the constants c and d that we are using. Okay, proofs by induction. Typically, they happen when you see a dot, dot, dot. Now, we summed two. You can actually sum as many functions as you like. If they are all of the same order, then the sum is also of the same order. In some sense, this seems counterintuitive, and actually it actually needs a proof. So why do you prove things? Well, it's not obvious that if you have an upper bound for each of the summands, that the total sum is also going to be bounded by the bound for each summand. What is critical here is that in the dot, 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 it's a finite sequence of functions. So perhaps I should circle this, because the theorem would not be true if the k could go as large as n. So k is a constant here. Somewhere in your proof you have to say that. So you can't really stretch this arbitrarily far. So that is important. Um, now, in the induction hypothesis, you can use the statement of the previous theorem. So you assume that it is true for k minus 1. There it is thus bounded. And you have then the result of the previous theorem. Um, so that's the so there are probably 4 sentences that you have to use. Use the statement proved by induction. You have the base case, 2 elements, that's the previous theorem. Then you apply the induction hypothesis, and you apply again the result of the previous theorem. Okay, asymptotic growth in a sum. So if we have now two non-negative functions such that one of these functions is has as upper bound the first function. So we have to show that the sum, we have actually now a tight bound for the function. So what does this actually say? That if you run an algorithm twice, and actually the second run, G, is bounded by the run of F, then actually you have a tight bound expressed in the running time of F. Okay, what do we have to show? So in some sense, this is good that we remember the definition. So we have the big omega. So we have to show that we have a lower bound. And also f plus g is bounded by the upper bound. Okay, so 2 sentences. So we have the lower bound. So g is here what we apply here is that it is non-negative. If g would be negative, that would not be true, but actually we subtract something. So naturally, f plus g is the lower bound. So now we have to show that the sum of two functions is the sum is bounded by the function of the sum. We have that previous theorem, and now I lost count. So this previous theorem is applied here. So g is O of f, and f is obviously O of f. So the sum is O of f as well. Okay, fourth exercise. Consider now a sequence of k non-negative functions and prove that if all of them are of the order of f, so of the same f. So actually what you do is you have your first f and then g1 up to gk, or gk minus 1 if you like, prove that generalization. Okay, if you have a finite sequence of functions, then actually the sum grows as rapidly as the most rapidly growing function in that sequence. That's what this function is. What this theorem is essentially saying. Okay, let's now look at some common functions. When we talked about polynomial growth, I said that you could focus on the leading monomial, and that's what this theorem essentially said. So we illustrated this in the first half of this lecture on two very specific quadratic polynomials. But here we're going to prove this by applying the properties, by applying the previous theorems. So a polynomial has a sum of many terms, monomials times coefficients. And we have that each of these monomials is bounded by the leading monomial. Okay, so notice that here what is implied is that n is positive. So we are considering positive integers, the size of the input. Okay, so we can find constants. In polynomials, we could have negative coefficients, so that's why the absolute value is taken here. So every term in the polynomial is bounded by the order of the leading monomial, the leading degree, monomial of the highest degree. And we apply the previous theorem, and we have the upper bound. Now, the last exercise for this lecture is to show that we essentially have tight upper bounds. Tight upper bound means that we have lower bounds as well. So that actually it is. So in some sense, you have to prove the big omega. And now it would be tempting to take the theorem here and simply replace the big O with the big omega and then try to do the same reasoning. And this would work. But be a little bit careful about there, because you want the big omega to be the leading monomial, and that might not go that well. So look for inspiration to the limit definition. Essentially, we have shown this on the quadratic polynomials in the first half. Okay, last comment on this slide. So nothing prevents you from having transcendental exponents, but even if that is actually not really a polynomial, it would still be polynomial running time. Okay, logarithms. We have consistently used the two logarithms in the big O. So in binary search, we use the two. We use the big O. The in the big O notation for binary search, we use the two logarithm. And you could say that in a computer science course, all logarithms are binary, but actually, it doesn't really matter. If you are in a hurry, then it's certainly not wrong to omit the base of the logarithm, because that's what this theorem here says. This theorem is just 2 lines long. If you recall that the logarithm is the exponent that you have to give to the argument, so that the base of that exponent is the number. So we can change of base. If we can go from base A to base B by the first sentence in the proof. And notice that what you divide by is a constant. And actually, the constant doesn't matter when you make a big O reasoning or a big omega reasoning. So omitting the base of the logarithm does change nothing in the asymptotic tight bounds. And this, I mean, you could say again, the bottom line is that logarithms grow so slowly that their base asymptotically does not matter. So that's why it's not, keeping in mind this theorem, it's not a lack of rigor if you omit the base in your logarithm. It's a different matter with exponential growth. So that's the last important point that I want to make in this lecture. The base of the exponential growth is very important, as was indicated already in the first tables in the first half of. It matters a lot if your base is 1.1 or if your base is 2 when you consider exponentials. So, um, what also means in notation, so if the capital N, if the input size appears as an exponent, then it grows faster than any polynomial. So that's what this theorem says. The observation that the base matters is because of this limit. So we have R and S. If R is larger than S, so you can take R2 as 1.1, then frequent exponentiation will go to infinity. If you flip the roles of S and over R, if R is larger than S, your limit will go to 0. So we consider always ratios, and the ratios in the limit, they must be constant. So this is another way of expressing this. If I hope at this time you are familiar with the limit notation, or if you were a good calculus student, you were never unfamiliar after your calculus course with limit notations. But here the point is that unlike logarithms, the base of the exponentials, they matter a lot. Okay, that's it for this pre-recording. I want to point at the first homework collection. So all exercises will be collected, because all exercises, no matter how straightforward they seem, they are important. So in the analysis, we try to be rigorous, we try to be precise. Many of these exercises require that you follow the notation on the slides. and adjust them and adapt them to the question that needs to be solved.